All right, everybody, Mr. Antonucci here, and we're at the fourth part for section 3 here, and we're going to talk about interpreting the integral as an accumulation function. So if f is a function that's continuous and non-negative on an interval a to b, then the definite integral exists and is equal to the area under the curve. So right here is what we're talking about. So from a to b. Well, suppose we define a function g to be g of x, and it's the definite integral from a to x of f of t dt. Now, since the independent variable is x for the function g, it's the upper limit of the definite integral. So we can interpret g as basically the accumulated area under the graph of f from a to whatever number x is. So that would be like this place. Okay. So if you could imagine X being able to slide back and forth, it would determine how much area has accumulated on that interval. Okay. So now if you suppose that F is not required to be non-negative, in other words, F could dip below the X axis, then F may have negative values or uh, non-positive values or negative values on some sub-interval um, between a and x. So this is the situation we have here in this third um, piece here. So notice that from a to c1 right here, f is non-negative. So as x increases from a to that point, the integral is going to accumulate in value and be increasing. Now, from C1 to C2, the function f has negative values, and so we're going to um, accumulate essentially negative values, which is going to cause g to decrease on the interval C1 to C2. And then at C2 to the end, the accumulation function g would begin to increase again. And so the net accumulation from A to B can end up being a positive number, a negative number, or even zero. So here we have the definition of an accumulation function. So if f is a function that's continuous on a closed interval A to B, the accumulation function g associated with f on that interval, closed interval A to B, is defined as the definite integral from A to x. Okay, so let's actually put this into practice here. So here we have the graph of sine t from 0 to 2 pi. And in part A, we want to find the accumulation function g associated with f over the interval 0 to 2 pi. So for part A, g of x is simply the definite integral from 0 to x of sine t dt. Now the antiderivative of sine is negative cosine, and we're going to evaluate that at 0 and x. So you have negative cosine of x minus negative cosine of 0. All right, so that ends up being negative cosine x plus 1, because cosine of 0 is 1, and you're subtracting a negative. So g of x is equal to negative cosine x plus 1. All right, so part B, if we want to find g of pi over 2, simply plug that in. It'd be negative cosine of pi over 2 plus 1. Cosine of pi over 2 is 0, so that would just be equal to 1. Graphically speaking, that would be the accumulated area from 0 to pi over 2. Now, if I go to 3 pi over 2, okay, that's going to be negative cosine of 3 pi over 2 plus 1. Again, cosine of 3 pi over 2 is 0. 0 plus 1 is 1. But watch this. That's the total accumulated area from 0 all the way up to 3 pi over 2 here. Okay, this region up here we know from 0 to pi over 2 has an area of 1. Since it's symmetric, this side of the hump would have an area of 1. This region down here also has an area of 1, but because it's below the x-axis, that's counted as negative change. So it would be an area essentially of 1, but counted as negative. So if you add all that up, 1 plus 1 minus 1 is 1. Okay. And then g of 2 pi would be negative cosine of 2 pi plus 1. Negative cosine of 2 pi is, well, cosine of 2 pi is 1. So you have negative 1 plus 1, which is 0. Now, if we go all the way to 2 pi, since you have symmetric regions, one is above and one is below, they offset each other, and the answer is 0. Okay, so all along I've been kind of interpreting the answers, but we can think about this a little bit more. Since the sine function is positive over the interval 0 to pi and negative from the interval pi to 2 pi, this can help us out. So the accumulation function, g, of f of t equals sine t increases from 0 to 1 to 2 as x increases from 0 to pi. Then it decreases from 2 to 1 as x goes from pi to 2 pi. So the net accumulation over the interval is equal to 0. Now, one thing I want to go back is I did not get g of pi. So g of pi is negative cosine of pi plus 1, which ends up being 2. Because cosine of pi is negative 1, the opposite of that would be 1. 1 plus 1 is 2. And that would be the area of this upper hump here, which is equal to 2. Okay. All right. So let's take a peek at one more example. We want to analyze another accumulation function. So this one is more from a graphical interpretation than just having the basic function. So this graph is the graph of f, little f, from -2 to 6. And g is defined as the definite integral from -2 to x of f of t. So for part A, I want to find g of 0. Okay, that's going to be the integral from -2 to 0 of f of t dt. All right. So it's this interval, -2 to 0. And if you look, the area of this region is just a triangle of base 2 and height 3. So it's 1/2 2 times 3, which equals 3. Now, there are no units involved here, so the answer is just 3. G of 4 is going to be the definite integral from -2 to 4 of f of t dt. Now, the reason we're starting at -2 is because the lower limit of the integral that defines g starts at -2. So if we go from -2 all the way up to 4, notice it's one big triangle, which is double the area of the first triangle we just found, and the top half of a semicircle of radius 1. So that's going to be 2 times 3. Okay, that's the triangle part, plus 1/2 pi r squared. Okay, so this is going to give us 6 plus pi over 2. All righty, and that is our exact answer. Again, if you needed the decimal one, you just dump it into a calculator. And then finally, g of 6 is the definite integral from -2 to 6 of f of t dt. So if we go all the way out to 6, it's everything we've done so far. So 6 plus pi over 2 plus this last triangle at the end. That's a triangle of base 2, height 2, so it's 1/2 2 times 2. But since the region is below, it's considered a negative net change over that interval. So g is actually decreasing, and this is how much it decreases over that interval. So you have 6 plus pi over 2 minus 2. So our final answer for this one right here is going to be 4 plus pi over 2. Okay, so that answers part A for us. Now, part B, determine where G is increasing or decreasing. So, um, first thing, to determine where it's increasing or decreasing, we got to find the derivative of G. So, um, G of X, not G of T. That's the derivative with respect to X of the integral from -2 to X of f of t dt. And all I'm doing here is just showing that the derivative of G by the fundamental theorem of calculus is equal to f of X. Okay, so G prime is greater than 0 um, from -2 to 4. Okay, because the derivative's graph, or f's graph here, is positive. So from -2 to 4, and then G prime of X is going to be negative, where f is negative, and that's going to be between 6 and 4. So by the increasing decreasing function test, G is increasing on the interval -2 to 4 and decreasing on the interval 4 to 6. Okay. Now, the last question kind of falls from that. If we want any local extrema only occur at critical numbers. Critical numbers are where the derivative is 0 or undefined. This function, the derivative would be undefined at 0 because there's a corner there. Excuse me. It would be equal to 0 at 2. It's not undefined there. This is the graph of the derivative, and it's continuous. So at x equals 2 and 4 would be our only critical numbers. At 2, the graph doesn't change sign since it's the graph of f, which is the derivative of g. You don't have any relative extrema there. The only one you have is at 4. And since the derivative changes from positive to negative, you have a relative extrema. Okay, in fact, you have a relative max at that point. So here's what we do. By the first derivative test, G has a local max at x equals 4. Okay, since G prime equals f changes from positive to negative at x equals 4. And then the max value is G of 4, which we got in the previous problem. So that's 6 plus pi over 2. All right. All right, guys, that was it for this one. Hope that was helpful to you. And as always, reach out if you have any questions. Take care.